So welcome back to 1.2-2. This is going to be the chemical properties of soils. And so as we talked about in the previous module, that soil, the soil texture is going to influence some of the things that are associated with our chemical properties. So what we'll talk about in this module is going to be how these soil colloids, the different types of soil colloids, and their role in basically nutrient retention. So this cation and anion exchange capacity. We'll talk about different clay mineral structures and understand where we get the charge from and kind of how those are set up and give us the structure, but also give us our chemical properties. So how we hold on to these cations and anions. And then finally, we'll talk about isomorphic substitution and pH-dependent charge. All right, so one of the things I don't want to do is I don't want to have you watch a video inside of watching a video. So I have posted this link inside of module 1.2 so that you can go back and watch. And this kind of gives you a very good overview of kind of a very generalized thought process towards soils. All right. So when we're talking about these soil colloids, really what we're talking about is like, remember I mentioned about the hydrometer method and those small particles that are kind of suspended that don't really settle out? Like that is what we consider to be soil colloids. And so the thing about these soil colloids is they're very small in size. They have a very high surface area. And if you watch the video, for the most part, they have positive and negative charges. And so when I'm thinking about soil, I really think of it like a magnet. And we have these negative charges that attract these cations. So cations being a positively charged ion. Anions are negatively charged ions. So from that video, for the most part, the overall net charge on soils is negative. There are going to be positive and negative charges associated with the soil, but unless you start getting into those highly weathered tropical soils, for the most part, the overall net charge is going to be negative. It is how negative. Is it a negative 8 centimoles of charge per kilogram, or is it a negative 18 centimoles of charge per kilogram that determines how many of these nutrients we can actually hold on to and provide to our plant? And so one of the things that is going to influence that's why formation is so important, because it's going to give us this mineral structure that is going to allow us to hold on to these minerals. And then also pH is going to play a role in that. So when I think about a soil structure or a soil colloid, what we have is this diffuse double layer. And so there's going to be kind of like, the way that I think about this could be, let's say this is a concert and this is the stage, and we have all of these people trying to fight to get right up next to the stage. Well, the same thing happens with our cations. So we have our cations and our anions with positive and negative charges trying to attract to this. And so if we have this positive attracting with that negative, then it's possible that this negative can also be kind of attracted to that as well. And notice that as we get further away from this soil colloid or further away from a stage, people are kind of, or our cations and anions are a little more spaced out. There's not as much attraction to kind of moving towards that. Everything's very loose. At this point, a plant can take either one of these nutrients up. It could get attached to another soil colloid. It might even just stay in solution. So just to have an understanding that this is really, for me, the way I think about this is it's all about magnets. It's positives and negatives. So when we have cation exchange capacity, this is going to be that interchange between cations and that surface of any negatively charged material. So positive and negative. And so the way that these cations are held to that soil colloid is a function of their charge and then also their hydrated radius. And we'll go over this in a moment. But for the most part, hydrogen and aluminum are strongly adsorbed to these negatively charged sites. Next, calcium. Calcium will be the next greatest cation that is held to the soil colloid. What that means is that it takes a lot of energy in order to displace that calcium. Next, we have magnesium 2 plus. Now we have potassium and ammonium that are equally adsorbed to soil colloids, and these are easily interchanged. So it might be that there's potassium on a soil colloid. We apply fertilizer that turns into ammonium. That ammonium will then displace this potassium, and that potassium might be taken up by the plant. And then finally, we have sodium. Sodium is not very attracted to soil colloids. And when I think of sodium, I'm thinking of salt. And so what happens is if we get enough sodium inside of this solution, we can actually displace all of these. And now we have a neutralized soil colloid, and we don't have any aggregate stability because this positive will be kind of pushing against another positive. All right, so now we're going to switch that over. And now we have anion exchange capacity. And so this is the interchange between anions and positively charged sites in our soil. If you recall from the video that we have both positive and negative sites in our soil, but for the most part, the overall net charge on soil is negative. So we need these positive sites in our soil in order to hold on to our phosphates and our nitrates and sulfates. And so here again, we have another kind of lyotropic series, except this is now for our anions. So we need both cation and anion exchange capacity in order to hold on to all of the nutrients that we need to supply our plants with. I want to talk about the difference between adsorption with a D and absorption with a B. So when I think of adsorption, if you were in class with me, I would probably have a piece of tape, and I would take the tape from my index finger and I will pull that off and I will put that on my middle finger, and I would pull it off and I put it on my ring finger. I would pull it off and I put it on my pinky finger. That is adsorbed. So adsorption, it can either be held or released, and then it could be attracted right to a soil to a negative charge right next to it. So adsorption is going to be attraction and release. Next, absorption is the movement into another substance or another component. So in class, if you were with me, I would have maybe lotion, or I might have hand sanitizer. And I would put that hand sanitizer on my hands and I would rub that until everything is absorbed into my skin. Now you can't pull that back out. That has been absorbed into another substance or into another kind of component. So when plants absorb with a B nutrients, the nutrient, let's say ammonium, has to be desorbed from that soil colloid and then absorbed with a B into the plant. That NH4 plus does not come back out of the plant until that plant decomposes. It is inside of the plant until it is released through decomposition. So adsorption is going to be This is going to be adsorption, the movement of these different molecules on and off of this negatively charged site. Absorption is going to be into plants. So adsorption is to soil colloids, absorption is into plants. So moving into the different types of soil colloids that we have crystalline silicates, and then we have non-crystalline silicates. And so for the most part, we're going to be talking about these four primary crystalline silicate minerals: kaolinite, smectite, and vermiculite. Maybe montmorillonite is in there as well. And then these micas. And so the way that these are put together, these are like the building blocks of soil. These are like electron microscopic structures that we're looking at. Some of the other ones that you might run into are going to be, you'll hear me talk about aluminum and iron hydroxides. These are going to be highly weathered soils that do not have much charge left to them. They are highly dependent upon pH, and there's a lot of aluminum and iron, obviously. And then finally, we have organic and humus. This is going to be our greatest cation exchange capacity. This is going to be the soil colloid with the greatest cation exchange capacity. We'll typically see these in histosols. They're going to have a high water holding capacity. So organic matter and humus actually kind of acts like a sponge. They can hold a lot more water than their weight. You all know the when you wash the car, there's like that ShamWow that can actually hold on to a lot more water than its weight. That is what organic matter is like. So organic matter is going to have both cation and anion exchange capacity, but the overall net charge is primarily going to be negative. All right, so just to look at some of these major properties, here is our silicate type. Remember that we're really only going to be focused on at least these 2-to-1 silicates and this organic. So notice that this humus has the greatest overall net charge, and this is in centimoles of charge per kilogram. So -100 to -500, meaning that it can hold on to up to 500 positive charges. Notice our kaolinite has a very small CEC, or a very low CEC. And if you watch the video, it talks about these low CEC soils being kind of like a cup. This is like the small cup that you get at the store, or maybe you get a small at a buffet, because you know you're going to go back several times to the drink machine. However, if we had something like a smectite or a vermiculite, this would kind of be like the very large cup, and you only go back once, and you've got a lot of negative charges that could hold on to a lot of those cations. So right here with this kaolinite, or maybe this smectite, is really going to determine how often you need to add these nutrients back to your soil, because they just can't hold as much. But if you have organic matter or humus in your soil, you can increase your cation exchange capacity. Those are probably the two big things that you should take from this chart. That our smectites and vermiculites are going to be the large cup. Our kaolinite is going to be the small cup. And that our humus is going to be like the extra large big gulp Slurpee from Buc-ee's. All right, so a little bit about the fundamentals of the silicate clay structures. So we have both a tetrahedral and an octahedral layer. And so you can see in this that tetra being 4, so tetrahedral layer is going to be comprised of 4 oxygens, kind of look like a pyramid. We'll see this in the next slide. And in the center of that generally is going to be silica 4 plus. And that silica 4 plus is going to have a nice balance with holding, kind of in the center, and being able to keep that in the center of that of this tetrahedron that you'll see in the next layer. I mean, in the next slide. For our octahedral layer, there will be 6 oxygens, and they will have either aluminum or magnesium in the center. All right, so let's take a look at that. Here we have our tetrahedron. We have our 3 basal oxygens and 1 apical oxygen. And in the center of that, we have our silica cation. When we move down here to our tetrahedral, we're going to have 6 oxygens, and we will have either aluminum or magnesium. These are actually hydroxides. And we'll have either aluminum or magnesium in there. This comes into play when we start talking about isomorphic substitution. So remember, we go back to the rock cycle. We have this magma that comes out of the earth as lava. It is going to cool, undergo that cooling, turn into an igneous rock. There may be some crystallization. And this is what we talk about when we mean crystallization. So for our 1-to-1 minerals, we're going to have 1 tetrahedral sheet on top of 1 octahedral sheet. And then we would just repeat this process continuously. So this is going to be 1-to-1 mineral right on top of each other. Tetrahedral, octahedral, tetrahedral, octahedral. For our 2-to-1 clay minerals, when I think about this, I'm thinking like a sandwich or maybe even an Oreo. So for this, we would have our tetrahedral sheet. We would have the stuffing or the octahedral sheet in the middle, and then that would be another tetrahedral sheet on the other end of that. So we would start to have this sheet with another sheet, and that would give us our 2-to-1 mineral structures. So for our 1-to-1 silicate clays, this is going to be kaolinite. Remember, kaolinite is going to be that very small cup, and that has a low negative charge that is only going to be on the edge of those sheets. Now, I mentioned isomorphic substitution, and this is going to be, it's possible that that silica 4 plus might be replaced by an aluminum 3 plus. And this goes all the way back to that rock cycle and the kind of the minerals that are available inside of that melted molten magma. And so it could be that it's silica, it could be that it's aluminum, not really sure. We weren't there when it was made. But this is what gives us kind of this 3 to 15 centimoles of charge per kilogram. And we'll look at this in a moment. So these can still be productive in agriculture. Just remember, it's that small cup. We're going to have to make several trips because we don't want to apply more than what that soil can hold. Typically, what we like to use kaolinite for are building foundations and road beds because it doesn't have very much movement. It's really not the ideal soil type that we would need. And we also, as far as production in agriculture, so it also serves another purpose as building and foundations. And if we go back and remember that this is a 1-to-1 to 1 to 1 to 1 to 1 to 1 to 1, that is going to give us a very stable structure. There's not a lot of room for movement, and we don't want movement when we're building houses or road beds. Okay, so here's another look at this. We have our tetrahedral here that is now attached to this octahedral. So our tetrahedral, octahedral, tetrahedral, octahedral. These hydrogen bonds are what stops that expansion. Like, because there's nothing else left, these remember that on our octahedral, there are going to be hydroxyls. And what that means is this is an oxygen and a hydrogen that is going to want to bind with the oxygen on that tetrahedral. And so because that hydrogen bonding is so much, one of the greatest bonds that we can have is hydrogen bonding, we're actually going to get that structure very tightly held, and there's nothing that's going to move that, or very little. So other, water or other cations can't really get in here and cause a little bit of like flexibility and movement. However, for our 2-to-1 silicate clays, these are going to be our expanding soils. And so they can kind of expand like a sponge. And so these are going to be our smectites, montmorillonites, and vermiculite. And they have this higher negative charge due to isomorphic substitution. And so you remember from our table, remember these are our smectites and vermiculites, our 2-to-1 silicates. Notice how much greater that net charge is compared to our kaolinite. And that's because they can expand slightly and increase that surface area. Notice the surface area difference as well. Okay, so the reason why that has that increased surface that increased surface area negative charge is because of isomorphic substitution. And so in the tetrahedral layer, we have a silica 4 plus, which is common, possibly replaced by an aluminum 3 plus. And so isomorphic substitution means similar size. It has nothing to do with the charge. The charge difference is what actually gives us the difference in CEC. And so if it was just a charge thing, we would not get any difference because there would be no difference in charge. But because this is a +3, we would have, when you see how we replace this, you'll see that we actually increase the number of negative charges on our soil. In the octahedral layer, aluminum 3 plus is going to be replaced by magnesium 2 plus. And so when we do this, if we were to have isomorphic substitution in both the tetrahedral and the octahedral layer, we would go from +4 to +3 and +3 to +2. We'll see this in the upcoming slides. We just know that our 2-to-1 clays are going to have a much greater cation exchange capacity, or we're going to have a bigger cup. All right, so here we have our 1-to-1 clay mineral. I'm sorry, our 2-to-1 clay minerals. This is our Oreo. We've got a tetrahedral and an octahedral, or 2 tetrahedrals and an octahedral in the middle. We have another 2-to-1 clay layer, and it rains, and now this water moves in and starts to kind of expand that like a sponge. When this water expands everything, now we have the potential for other cations to be adsorbed with a D to these oxygens in this tetrahedral. One of the other silicate clays is going to be a mica. And so micas, we have isomorphic substitution, but we also have potassium fixation. And so inside of this structure, what we find is that the potassium ion fits perfectly inside of the void underneath this tetrahedral layer. Get that. So we have this tetrahedral layer that has this void where these potassiums can fit in there. And when we have this, this now takes the charge away. So remember previously in a 2-to-1 layer, we would have water that comes in here. Well, if the potassium fits inside of the half of the bottom of this, it fits in the half of the bottom of that and kind of locks that together. The charge is now neutralized. And so nothing else can come in and change that. So when I'm thinking micas, I'm thinking K fixation, mica, potassium, K fixation. When you do this on the quiz or on the exam, this one should be a dead giveaway. It's the one that has the potassium in it. Mica's K fixation. We also have chlorites, and the thing about the chlorites is we're going to have our Oreo, and our Oreo. Oh, get back. Our Oreo and our Oreo, and we're going to have an octahedral layer that kind of comes in and again takes away the outer charge on the outside of this tetrahedral layer on both sides of those. So we're going to basically have an even stronger lock than we would have with our micas. Micas are 2-to-1, chlorites are 2-to-1-to-1. All right, so just a look at everything overall. You're going to need to know this on the quiz and the exam. Here we have our kaolinites. This is just a 1-to-1, 1-to-1. It has no swelling potential because all of the charges along this tetrahedral layer are taken up by this octahedral. Next, what we have are micas. So the mica and potassium, when I see this potassium there, I'm going to instantly know that this is going to be a mica, and I am not going to have any expansion because these positive charges here are going to fulfill the potential negative charges on each of these tetrahedral layers. Next, we have vermiculite. This is going to be moderate swelling. The way that I will go about knowing these is that montmorillonite is going to have the montmorillonite is going to have more expansion. And then finally, we have our chlorite, which is going to be, this should actually be a 2-to-1-to-1 because we have a 2-to-1 layer, another 2-to-1 layer that is being held together by this octahedral layer. So chlorite, this should actually be 2-to-1-to-1.